So let's imagine a motion of the following kind. Say there is a certain fixed point O, and there is a particle at this point at a certain instant of time having a velocity v naught to the right, having a velocity v naught to the right. And at this instant, at this juncture, the force acting on the particle while it's at O is 0. Stand by. So there is this particle at O having a velocity v naught to the right, and while it's at O, the force acting on the particle is 0. It has no acceleration at this instant at O. Now, despite no force acting on the particle, it moves to the right by virtue of inertia, and while it moves to the right, the moment it deviates from O and moves to the right, there is a force that triggers on the particle, there is a force that acts on the particle, and the direction of that force is always towards O. The direction of that force is always towards O, and the force grows in magnitude, grows in stature, while the particle keeps moving to the right. The force acting on the particle, the moment it slips away from O, is always directed towards O, and the magnitude of the force will depend on how far it is from O. So, as it moves further and further away from O, the magnitude of the force grows, and it's in stark opposition with the velocity of the particle, right? So, what does this force do? This force kills the velocity because it retards the particle. It kills the velocity, and when the velocity of the particle gets killed, as long as the particle has a velocity, no matter how small, to the right, and no matter how large the force acting on the particle is, as long as the velocity does not get reduced to 0, the particle will keep moving to the right, Now, the mathematical description of this force, say this O is the origin of coordinates, and to the right we have the positive direction of the x-axis along the line of motion of the particle. This is an arbitrary instant where the particle is at x. That means it's at a distance x from O, x is the coordinate of the particle, locating the particle. So the algebraic description of the force acting on the particle is, let's say, a constant k times x with a negative sign. The negative sign would ensure that the force is always towards O, because when x is positive, f becomes negative. F becomes negative means it has to be in this direction, because by our very convention, everything measured in this direction is positive, things measured in this direction would be negative, right? And at some instant when the particle, let's say, is at this x, where x is negative, so f would then become positive and the force will still be towards O. So this description only guarantees, the minus description only guarantees that the force is always directed towards this fixed position, O. We would refer to this fixed position O as the mean position or the equilibrium position. Equilibrium position does not mean it has to be at rest. All that it means is it's unaccelerated at this point. The acceleration of the particle at O ought to be 0. The net force acting on the particle at O ought to be 0. Right? The particle could be subject to a combination of forces. And what I'm talking of is the net force of acting on the particle at all. That should be 0 at the equilibrium position or the mean position. Now, not only this, we will also assume that the nature of this force is conservative. We will also assume that the nature of this force is conservative. We can then imagine a force field along the x-axis, because as x varies, the force varies. As x varies, the force varies commensurate with this condition. So there is a force field in the x direction. There is a force field in the x direction. And with every conservative force, you can associate a potential energy. With every conservative force, you can associate a potential energy. And like I have told you before, since all the variations occur in the x direction, the potential energy of the particle, the potential energy of this particle or this system would be a function of x, right? And like I have discussed in my classes on work power energy, this force is measured by the rate of change of u with x. This force is measured by the negative of the rate of change of u with x. That's how I define my u. That's how we define our u. Yes or no? So then this would enable computation of u as a function of x. Right? And then we go ahead and integrate this. Integral du would be u. This would be half kx squared plus a constant c of integration, Now, this c is really an arbitrary constant. The value of this c can be uniquely determined if we choose a reference point for the potential energy. That means if we say that, well, a certain x equal to x1 corresponds to potential energy u equal to u1, then the value of c could be obtained. So might as well, and you know, there are no rules or laws governing this. The only thing, the unsaid rule is try to make it as simple as possible, right? So in our attempt to make life simple, the expression for u looks simple. What we do is we choose this point, which is x equal to 0, as the 0 of potential energy. X equal to 0 as the 0 of potential energy. So when x is 0, u is 0. Right? And that would cause c to be 0. That would bring c to be 0. And which then would mean that potential energy at any given x for the system is going to be half kx squared. Now, this k is called the force constant of the motion. This k is called the force constant of the motion. And is an inherent property of the system executing this kind of motion. It's an inherent property. K is an inherent property. Now, once we have things in place, what really happens is, as the particle keeps moving further and further away from the origin, x goes on increasing, so potential energy goes on increasing, and therefore you would expect the kinetic energy to diminish, right? So the velocity of the particle reduces, the velocity decreases as x increases in magnitude. As x increases in magnitude, the velocity will decrease. Why? So as to preserve the total mechanical energy of the system. What's the total mechanical energy of this system? At any given instant of time, when the particle has a velocity v and the particle is at x, the total mechanical energy is given by half kx squared plus half mv squared, where m is the mass of the particle subject to such a variation. In this kind of a motion, there is an interplay between v and x, right? So the interplay is in a manner that this, so x would vary, v would vary, but it's going to preserve this sum all the time. This would remain the same all the time. This would, at any given x, if the velocity of the particle is known, then you would know the total mechanical energy embedded into the system, total amount of mechanical energy. We will assume that there are no dissipative forces acting, so that the total mechanical energy remains unaltered. Okay, now coming back to this, in a force domain, F equal to minus kx, that's the force acting on the particle. So while the particle keeps moving to the right, this x grows. So the retarding force, realize that this is a retarding force. It's always directed towards O. When the particle is moving towards the right, it's a retarding force, right? So this force grows in magnitude and it retards the particle more and more as the particle keeps moving to the right, right? Which means it kills the velocity, this force kills the velocity, and it kills the velocity at a faster and faster rate because the retardation keeps growing. So if in the first, while the particle is moving to the right, if in the first 1 second, the velocity gets killed by 1 meter per second, then in the next 1 second, it will get killed by more than 1 meter per second because there is greater amount of retardation as the particle has moved away, right? So then, suppressed by this retarding force, you would eventually find the particle to arrive at a point Q, where the velocity of the particle would eventually become zero. Where the velocity of the particle would eventually become zero. And then at this juncture, the force acting on the particle will be proportional to the length OQ, will be proportional to the length OQ. This point Q is called the rightmost extremity of the motion. It's called the rightmost extremity of the motion. This point Q is the rightmost extremity of the motion that we are going to discuss. The particle can't go any further to the right. In this case, the particle can't go any further to the right. The particle is subject to a leftward force then, whose magnitude is going to be k times OQ, whose magnitude is going to be k times OQ. The particle then starts to move to the left under the influence of this force, whose magnitude is k times OQ initially, and therefore, under the influence of this force, the particle gathers velocity leftwards. The particle now gathers velocity leftwards. In this case, the direction of the force and the direction of the velocity the same, right? And therefore, the particle will accelerate. The particle will accelerate. So while the particle keeps moving to the left, its velocity will grow. Its velocity will grow. But then the acceleration will reduce. Why? Because x reduces when the particle moves to the left towards the mean position. The acceleration is going to reduce, so the velocity will grow, but at a smaller and smaller rate. Which means if in the first 1 second of this motion, the velocity has grown by 1 meter per second, then in the next 1 second, it will grow by more than 1 meter per second. Less than 1 meter per second, it will grow by less than 1 meter per second. So, in any case, it will still keep growing. It will still keep growing. The x will keep reducing and v will continue to grow. And the particle will arrive at this point O, with zero potential energy, because x becomes zero now, and zero potential energy, that means it must have had the same kinetic energy, so it is commensurate with conservation of energy. It's going to have a velocity v naught leftward. So there's the same kinetic energy. While it arrives at O, x is zero, so zero potential energy. So the kinetic energy is what it always was, half m v naught squared at this point. So it's going to become velocity v naught leftward. Now, having arrived at this point, the particle now drifts to the left. After a while, it arrives at a certain x with a velocity v leftwards. With a velocity v leftwards. The force acting on the particle now is rightwards, still towards O. So the particle will now get retarded. And it will keep getting retarded more and more aggressively. While the particle goes to the left, x will increase. So the extent of retardation will increase. So the velocity will get killed at a faster and faster rate. Realize that everything that happened to the right is now going to happen to the left. The same kind of motion will be replicated to the left. And therefore, you would expect at a certain point P, the velocity of the particle to again become zero, right? And again, from symmetry considerations, since the same kind of motion was executed to the left, you would expect OQ to be equal to OP, right? And this length, OP equal to OQ, is called the amplitude of motion. Which is the maximum displacement that the particle executes from the origin. Maximum displacement with respect to the origin, that's the amplitude of motion. Now, what you can then see and conclude very readily, this is the mean position or the equilibrium position. There is a leftmost extremity, A units away from O to the left, and there is a rightmost extremity, Q, which is A units to the right from O. The motion at all times will remain confined to the region PQ, will remain confined to the region PQ. So the motion obviously is bounded. The motion is bounded. And obviously, since it moves to and fro, back and forth, it's also oscillatory. It's bounded, it's oscillatory. And very shortly, I'm going to tell you why it's periodic as well. And I'll tell you what I mean by the motion being periodic. Now, the kinematic status of the particle, the complete kinematic status of the particle at any given instant of time is determined by two things. Number one, where the particle is located. Now, that means x. Now, once x is known, v would be uniquely known. The speed of the particle would be uniquely known, but not the direction. So, when I say the state of motion, then I need two things to completely define the state of motion at any juncture between P and Q. The x, the position, would be uniquely determined, and then not just the speed, but rather the velocity v. That means at x, well, the particle could have been moving to the right with a velocity v, or could have been moving to the left with a velocity v. These are two different states. X with a v to the right or x with a v to the left are two different states, right? So, when I talk of the kinematic status of the particle, then I mean x and the velocity along with the direction. That means whether it's moving to the right or it's moving to the left. Now, at the same x, the particle could have had a velocity to the right or could have had a velocity to the left. For example, when the particle was moving rightward, heading for Q, then it would have a velocity v to the right. But when it arrives at the same x, it will have the same kinetic energy, but now its velocity would be v to the left, right? Now, when I say that the motion is periodic, what I really mean is the same kinematic status, that means the same x-v combination, the same x comma v combination is replicated after equal intervals. The particle is at the same x with a velocity in the same direction at equal intervals of time. That's what I mean by periodicity of motion. That's what I mean by periodicity of motion. You know what I'm saying? The minimum time in which the same x and the same v get completely and uniquely replicated is called the time period of motion. It's called the time period of motion. The time in which the same x and the same v get completely replicated, the minimum time in which the same x and the same v gets completely replicated, that is the kinematic status gets completely replicated, is called the time period t of motion. That's the time period of motion. And if one can find a t commensurate with the motion, then the motion is periodic. If one can find a certain value of t, finite value of t, uniquely, then the motion is periodic. Now, physically then. So I will demonstrate that the motion which I have just described is periodic. So for the time being, assume that, well, there is a period associated with the motion t. So at a certain instant t equal to t naught, at a certain instant t equal to t naught, the particle had a velocity v to the right and was at x. It moves to its rightmost extremity, turns around, comes back to x. Now when it comes back to x, its x is replicated, but its velocity is not replicated. Speed is replicated, but not its velocity, because velocity is v leftward. So this is not the time for the time period. This is for sure not it, because the same x and velocity combination is not replicated. X and speed combination is replicated, right? So then the particle goes to the right, arrives at the leftmost extremity, then turns around, comes back to this x. Now when it comes back to x, it has a velocity v to the right. So the time in which this complete cycle is executed is one time period. The time in which this cycle is executed is one time period, also called the fundamental period of the motion, Now, one observation, if there exists a t for this, then do you realize that in a journey that elapses one full time period, all points between P and Q, to the exclusion of P and Q, all points between P and Q, excluding P and Q, are crossed exactly twice. In a full time period, every single point, barring the extremities, is crossed exactly twice. Now, if you look at the extremities, that means crossed twice means that point is crossed at two different instants of time. For example, this point is crossed at t equal to t naught, and then after a while, the same point is crossed at, let's say, t equal to t naught plus delta t, right? So at two distinct instants of time, the same point is crossed in a full time period. As far as the extremities are concerned, they are also crossed twice. They are crossed at coincident instants of time. They are also crossed twice, but then those instants of time are not distinct but coincident. So mathematically speaking, every point is obliged exactly twice. The extreme points are obliged at two coincident instants of time. Other points are obliged at two distinct instants of time in a full time period, right? And a full time period is about what we say is a full oscillation is a full oscillation. This is a full oscillation. This is a full oscillation. Complete. Whatever is done in one full time period is referred to as one full oscillation. So in one full oscillation, every single point is crossed exactly twice. And if t seconds is the time taken for one full oscillation, if t seconds is the time elapsed for one full oscillation, then the number of oscillations per second is going to be 1 by t. Then the number of oscillations per second is going to be 1 by t. Per second. Number of oscillations per second is going to be 1 by t. Because see, 1 by t means what? 1 by t is seconds per oscillation. Seconds per oscillation. It's seconds per oscillation. So 1 by seconds per oscillation is like oscillations per second. Oscillations per second. Right? So 1 by t would give you the oscillations per second, and this fact is referred to as the frequency of the oscillator, or the frequency of the oscillator. This 1 by t is the frequency of the oscillator. T is the time period, n is the frequency of the oscillator. Now, it's not essential that the mean position has to be the origin. It's not essential that the mean position of this oscillation has to be the origin. The mean position can be some x equal to x naught. The mean position can be some x equal to x naught. In which case, the particle will move a units to the right of x naught and would move a units to the left of x naught. That means this rightmost extremity is going to be a plus x naught, the leftmost extremity is going to be x naught minus a. X naught minus a is going to be the leftmost extremity. Now, in a situation of this kind, at some instant when the particle is at x, the force acting on the particle will be minus k times, k is the constant of proportionality, k times this distance. This distance is x minus x naught. This displacement is x minus x naught. So now instead of having x, you have x minus x naught. So this is like f equal to minus kx plus kx naught. Minus kx plus kx naught. But this kx naught is like a constant c. Is like a constant c. So this is like minus kx plus c. So while f equal to minus kx is simple harmonic motion, with origin being the mean position, f equal to minus kx plus c is also simple harmonic motion, but in this case the origin is not, the mean position is not the origin. The mean position is not the origin, right? In this case, the mean position is the origin. In this case, the mean position is not the origin. Now, what characterizes the mean position? The mean position is characterized by the fact that at that position, the force acting on the particle must be zero, right? So, let's say if a particle is subject to a force F, which is minus kx plus 5. This is simple harmonic motion for sure. This is simple harmonic motion for sure. But then the mean position is given by x such that minus kx plus 5 equal to 0 or x equal to 5 by 8. This is the mean position. K is inherent to the oscillator and would be given to you or would be calculation worthy, right? So then, given K for the oscillator, the mean position could be obtained by simply converting f to 0 and obtaining the value of x that causes f to be 0. So in this case, this is the mean position. X equal to 5 by k is the mean position. F equal to minus kx, x equal to 0 is the mean position. But both are simple harmonic oscillations. Both are simple harmonic oscillations. Now, choice of origin will not alter the fundamentals. What are the fundamentals of the motion? The fundamentals of the motion revolve around, let's say, the time period of motion, which we would see very shortly, would emerge out of the K. The force constant would tell you the time period of motion for a given particle which is executing that motion, having a certain mass. So, whatever fundamentals we arrive at with the origin being the mean position would be the same as the fundamentals with the origin not being the mean position, some other point being the mean position, right? So then, let's make life simple. Assume that the equilibrium position or the mean position is the origin and that the particle is subject to force characteristic F equal to minus kx. Oh, the mean position is the origin as well. Everything measured to the right with respect to O would be positive. Everything measured leftwards would be negative. Rightward is the positive direction of the x-axis. The rightmost extremity is A0. The leftmost extremity is minus A0. And O is 0, 0. At x equal to A, the velocity is 0. At x equal to A, the velocity is 0 because that's why it's the rightmost extremity, right? So the potential energy at this point is 0 because half k, the kinetic energy is 0, sorry, the kinetic energy is 0. The particle has only potential energy at this point. So the potential energy at this point is half k squared. Potential energy at this point is half k squared. The kinetic energy here is 0. So the total mechanical energy at A0 is half k squared. That means this must be the total mechanical energy anywhere. This must be the total mechanical energy anywhere. At some instant when the particle is at x and has a speed v, the total mechanical energy is given by half kx squared plus half k plus half mv squared. And this must be the same as the total mechanical energy at the extremity, which is half k squared. Right? And now you can get mv squared as k into a squared minus x squared. And this I can write as v equal to root k by m into a squared minus x squared. Right? Yes or no? Now it's customary to call k by m as some omega square. We will arrive at the physical meaning of omega in a while, but for the time being, just imagine this to be merely mathematical. Right? So then v would become like omega root a squared minus x. So the speed of the particle at any given x is given by omega root a squared minus x squared. This also conforms to the boundedness of the motion because root a square minus x square would be defined only when x lies between plus minus a. Because if x is greater than a or x is less than minus a, this quantity will become negative and the square root of this will no longer be real. So this also suggests very categorically that the motion is bounded, right? Not only that, as the magnitude of x goes on increasing, the velocity goes on decreasing in magnitude. So the velocity obviously would be maximum when x is the minimum. That means at the main position where the potential energy is zero, kinetic energy is maximum, and you will have the maximum velocity of the particle. So maximum velocity will always occur at the mean position and would be omega times, put x equal to 0, would always be omega times a, where a is the amplitude of motion. A is the amplitude of motion. Now, realize that v at this x will always be given by rate at which x changes with time. Rate at which x changes with time would give you the velocity v, which is like omega root a squared minus x squared, right? And then we separate the variable gx by root a squared minus x squared is going to be omega dt. Right? And then we carry out an integration. We will learn in integration that this is sine inverse x by a. This is sine inverse x by a. Is omega t plus a constant phi of integration. Right? When you integrate, omega will come out. Omega is root k by m will come out, and therefore omega t plus phi, where phi is a constant of integration. It's a constant of integration. And this constant of integration phi is also called the phase constant for the motion. This phi is also called the phase constant for the motion. For the oscillator. This would then mean that x by a is sine omega t plus phi of x is a sine omega t plus phi. X is a sine omega t plus phi. So that's how the displacement with respect to the mean position varies with time. That's how the displacement with respect to the mean position varies with time. X as a function of time. This will give you x as a function of time. If I differentiate it a second time, first time, I get the velocity. X dot would be the velocity, which is the rate at which x changes with time. When I differentiate it the first time, then I get a times omega cos omega t plus phi. That's the velocity at any given instant of time t. And if I differentiate it again, then I get the acceleration, which would be x double dot, differentiating x twice with respect to time. And that's going to be minus a omega squared sine omega t plus phi. I hope you've not forgotten your chain rule. Minus a omega squared sine omega t plus phi. Now, for sure, realize that when we started with, we had this f equal to minus kx. Therefore, the acceleration would have been minus k by m into x. That would have been the acceleration. But k by m we have referred to as omega squared. So this is how acceleration varies with x. This is how acceleration varies with x. Yes or no? And a versus x would be a straight line whose slope would be minus omega squared. Right? So if I plot a versus x, then I get a straight line. x remains bounded between minus a and plus a. At x equal to 0, which is the mean position, the acceleration is going to be 0. So this is how acceleration varies with x. Obviously, when x is negative, acceleration is going to be positive because it's directed rightward. When x is positive, which is here, acceleration would be negative, it will be directed leftward. Right? Now, can I write this out? See, f equal to minus kx plus a constant is a simple harmonic motion. Is a simple harmonic motion, but the mean position is not the origin. If this constant is not zero. So then in this case, the acceleration would become, if I divide by mass, I'll get the acceleration. So minus k by m, that means minus omega square x plus constant by a mass, by the mass will also be a constant. So this would also characterize simple harmonic motion with the acceleration not becoming zero at the origin, right? Now, various things would fall in place and they would actually mean the same. And as beginners, it must be spelled out very clearly to you. So what I'm going to suggest. Look, in a typical motion, I got x equal to a sine omega t plus phi. X equal to a sine omega t plus phi as the displacement time characteristic. This also guarantees that this expression lies between plus a and minus a. So the motion is bounded. Now, this space constant phi. What is the space constant? There is a particle oscillating between limits p and q. There is a particle oscillating between limits p and q. And at the behest of a professor who's carrying out this experiment in the lab, there are 3 students entrusted with the job of computing phi, right? They have different sleeping schedules, so they come at different instants of time and compute the value of phi and present it to the professor. The first joker wakes up from deep slumber and at the instant he makes an observation about this particle. He finds that the particle is at O and is heading to the right. He finds that the particle is at O and is heading to the right. Right? Now with this data, he wants to be able to compute the value of phi, the phase constant for this oscillation. So the moment he starts observing, he would deem it fit to call as the instant of time t equal to 0, right? So he would choose to say, well, this is t equal to 0 as far as this student is concerned, this observer is concerned, right? So he says, well, at t equal to 0, x was 0. He readily says that at t equal to 0, x was 0. So if you put x equal to 0 here, and t as 0 here, this is a sine phi, right? Now, that gives me sine phi equal to 0. That gives me sine phi equal to 0 and phi therefore could be 0 or pi. Phi therefore could be 0 or pi. So now he would not go and tell the professor it's either 0 or pi, right? He would have to give a definite answer to the value of phi. So he observes that the particle at this instant has a velocity to the right, that means has a positive velocity. So he differentiates this and says velocity at any given instant of time is going to be given by a omega cos omega t plus phi at time t equal to 0. The velocity is a omega cos phi. Velocity is a omega, right? And is positive because the particle is observed to be moving to the right. So it's positive, which means cos phi would be greater than 0. So phi couldn't have been pi. Phi therefore must have been 0 because cos phi equal to pi would render cos phi negative, right? So phi must be, with this data and this data in place, phi therefore must be 0. Phi therefore must be 0. Right? So if phi is 0, goes back to this equation, conveniently plugs in phi equal to 0, giving x equal to a sine omega t as the displacement time characteristics of the motion. Displacement time characteristics of the motion. Yeah. Student number 2. So this is the output produced by student number 1, right? Student number 2. He arrives when the particle is halfway between O and Q. That means when the particle is at x equal to a by 2. He starts to observe this oscillator when the particle is at x equal to a by 2 and let's say is moving to the right. Let's say is moving to the right. So what he would describe as the motion is like, well, at t equal to 0, x is a by 2. At t equal to 0, x is a by 2 is what he would suggest. So in this equation, he plugs in x equal to a by 2 and t equal to 0. X equal to a by 2 and t equal to 0. So that gives him a by 2 equal to a sine phi, right? Sine phi therefore is half. Phi could have been 30 degrees or 150 degrees. Phi could have been 30 degrees or 150 degrees. Right, so it could have been pi by 6 or 5 pi by 6. Now, to uniquely determine phi, he looks at this equation, plugs in t equal to 0 in this to get velocity at time t equal to 0 as a omega cos phi. Right? And since the particle had a velocity to the right, so this must have been positive. This must have been positive, causing cos phi to be positive, yes or no? And cos phi could have been positive, not in the second quadrant, but in the first quadrant. So this data and this data combined together would give me phi equal to 30 degrees. Phi equal to 30 degrees, yes or no? So he says, well, phi is pi by 6. Not pi by 6. So he plugs in phi equal to pi by 6 and he says the displacement time characteristic a sine omega t plus pi by 6. That's student 2. And then there was student 3. who wakes up later and finds that the particle is at the rightmost extremity when he starts observing the particle, right? That means at time t equal to 0, the particle was at x equal to a. At time t equal to 0, the particle was at x equal to a. So in this, plug in t equal to 0 and x equal to a, you get a equal to a sine phi. A equal to a sine phi. Put x equal to 0 when t is 0. That gives me a equal to a sine phi. So that gives me sine phi equal to 1. And phi therefore is pi by 2. Phi therefore is pi by 2. So then this gives me x equal to a sine omega t plus pi by 2. But sine theta plus 90 degrees is going to give me cos theta. Cos theta. So this is like a cos omega t. So he describes the same motion as x equal to a cos omega t. Now, the very simple conclusion which you would have arrived at independently by this time is that there is nothing God sent about phi. There is nothing fundamental about phi. See, it's the same oscillator with the same time period, with the same frequency, right? Oscillating between the same limits. But then, different people come down to you and report different values of phi. So, phi, the phase constant, is really the observer's domain. The phase constant phi is really the observer's domain. There is nothing inherent or fundamental about phi. It's only mathematical. There is nothing physical about phi. It's only mathematical. It does not throw light on the nature of motion. It just throws light on the observer. It tells you about the observer, not about the motion. You know what I'm saying? It just tells you when the observer came and started taking data from it. It doesn't tell you anything about the oscillation. The oscillation has fundamentals which are related to the amplitude of motion, the time period of motion, the frequency of motion, right? But not about the phase constant. All these descriptions of x versus time are talking about the same motion with the same amplitude, the same frequency. But then the cosmetic looks are different, which means there is actually nothing different in all these descriptions. They all lead to the same road, right? So, for sure, the conclusion is that phi is only mathematical and is the observer's domain, right? Now, even though phi is called a phase constant, this description, which is x equal to a sine omega t plus phi, this omega t plus phi is time dependent. Time dependent. Phi is observer's domain. Omega t plus phi would be different at different t's. And this entire omega t plus phi is called the phase of the motion. This is called the phase of. Phi is a phase constant. Phi is a phase constant, but omega t is the phase. The same particle will be described by different phases at different t's for a given phase constant phi. For a given phase constant phi. So this entire thing is the phase, whereas phi is the phase. Here. Now, coming to a very pertinent issue. Issue of the time period. The time period of motion. Like I said, t, the time period of motion, is the smallest time in which the x-week combination is completely uniquely replicated. Right? The particle arrives at the same position with an identical velocity, in the same speed and the same direction of motion. Time over which this happens is the time period of motion. Realize that for an oscillator, x is given by a sine omega t. This could be written as a sine. So this is x at any given instant of time. X at any given instant of time. This could be written as x equal to a sine omega t plus phi plus 2 pi. Yes, no? Sine 2 pi plus theta is the same as tan theta, right? Which then could be rewritten as omega t plus 2 pi by omega plus phi. Do you realize that if this is x at t, then this is x at t plus 2 pi by omega? Yes or no? If this is x at t, then this is actually x at t plus 2 pi by omega. This argument is identical to this argument. Only thing is t has been replaced by t plus 2 pi by omega. Do you realize that? So if this is x at t, this is x at t plus 2 pi by omega. So one thing that's guaranteed is that x at t, the displacement at an instant of time t, is the same as the displacement at an instant of time t plus 2 pi by omega. Yes or no? Now, that means in an interval of time 2 pi by omega, x for sure is replicated. Right? In an interval of time 2 pi by omega, x for sure is replicated. We want to see if in the same time v is also replicated. We want to check if in the same time 2 pi by omega, v is replicated or not. That means, is v at t the same as v at t plus 2 pi by omega? If that happens, then we know that in an interval of time 2 pi by omega, both x and v get completely replicated. In which case, 2 pi by omega would be rendered the time period of motion. Right? So, the next thing is only a check to be performed. V at any given instant of time t is like a omega cos omega t plus phi. Yes or no? Which is like a omega cos omega t plus phi plus 2 pi. Right? Which is the same as a omega cos omega t plus 2 pi by omega plus phi. Right? Is it not? So this is v at t. This is v at t plus 2 pi by omega. Yes or no? This is v at t. This is v at t plus 2 pi by omega. Clear? So v at t is the same as v at t plus 2 pi by. That means in an interval of time 2 pi by omega, both x and v get completely replicated, meeting the requirements of a full time period to complete oscillation. Right? So can I not conclude that t equal to 2 pi by omega is the time period of motion, T equal to 2 pi by omega is the time period of motion. Where omega be written as root k by n. Yeah. So this I could write as omega equal to 2 pi by t. Omega equal to 2 pi by t. Very clearly, this 2 pi is in radian and t is in second. So omega would be radians per second. Omega would be radians per second. And 1 by t would be the frequency of the oscillator. 1 by t would be the frequency of the oscillator. So this is going to be 2 pi n. Omega is going to be 2 pi Here, this omega is commonly referred to as the angular frequency of the oscillator. Is commonly referred to as the angular frequency of the oscillator. This is called the angular frequency of the oscillator, measured in radians per second. N is the frequency, and since omega and n are separated by a factor 2 pi, which is like angular, which is an angular property, so it's called angular frequency. It's called angular frequency, right? Essentially, what I told you was every time you find that the acceleration is minus a positive constant, let's say omega squared times x, you can readily conclude that the motion is simple harmonic. Every time acceleration is minus omega squared times x, the conclusion is the motion is simple harmonic. Now, if I had x equal to a cos omega t plus phi, for example, and I want to check if this motion is simple harmonic or not. I want to check if this motion is simple harmonic or not. I differentiate one x dot, which is minus a omega sine omega t plus phi, right? If I differentiate a second time, I get x double dot, which is acceleration. X double dot is acceleration, which would be minus a omega squared cos omega t plus phi, right? Hey, but a times cos omega t plus phi is x, so I have a, which is x double dot, minus omega squared times x, and the conclusion is that the motion is simple harmonic. Simple harmonic. Not only that, even if a turns out to be minus omega squared x plus a constant, this motion will also be simple harmonic. This motion will also be simple harmonic. Yes or no? The only thing is, in this case, a does not become 0 at x equal to 0. A becomes 0 at x equal to c by omega squared. So the mean position is different, but this motion is also simple harmonic. Now, suppose I have x given by some constant p plus a cos omega. Suppose I have a motion described by x equal to p plus a cos omega t, and I want to check if it is simple harmonic or not. Then, well, I differentiate one time, I get x dot equal to minus a omega sine omega t. I differentiate a second time, x double dot equal to minus a omega squared cos omega t, right? But this a cos omega t could be written as x minus p. So this is minus omega squared into x minus p, right? So this gives me like a x double dot, which is the acceleration, as minus omega squared x and plus omega squared p, which would be a constant c. So this motion is also simple harmonic, with angular frequency being omega. Angular frequency being omega. Similarly, if I had like a sine omega t, then also it's going to be simple harmonic. What if I had x given by a cos square omega t? What kind of a motion would this be? X equal to a cos square omega t. Instead of cos omega t, I had a cos square omega t. Now this I could write as a by 2, 1 plus cos 2 omega t. Cos square theta is half of 1 plus cos 2 theta. I differentiate one time x dot. I get minus a by 2 into 2 omega sine 2 omega t. Right? And then I differentiate a second time to get the acceleration x double dot as minus a omega into 2 omega cos 2 omega t. Right? Hey, but a by 2 cos 2 omega t can be written as x minus a by 2. Look at this. Look at this. In this, we very clearly have 2x equal to a plus a cos 2 omega t. From this equation, 2x equal to a plus a cos 2 omega t. Which means what? The a cos omega t could be written as 2x minus a. So the a cos omega t could be written as 2x minus a right here. So x double dot is like minus 2 omega squared into a cos 2 omega t, a cos 2 omega t, sorry, this was a cos 2 omega t as 2x minus a. Yes or no? Which would give me again the same kind of thing. X double dot is minus 2 4 omega squared x plus a constant. So this will also be simple harmonic. This will also be simple harmonic. The only difference is that the moment I say x equal to a by 2 into 1 plus a by 2 cos 2 omega t, the angular frequency now will be 2 omega instead of going to be 2 omega, right? Which of course could have been inferred from this. Realize that x equal to p plus a cos omega t is the same as, this is the same as p plus a by 2 cos 2 omega t. So if this is simple harmonic, right at this stage we could have concluded that the motion is simple harmonic without doing all this, right? Similarly, if someone said x is a sine square omega t, okay, in this case, what's the amplitude of motion? A, right? So in this case, what's the amplitude of motion? A by 2. A by 2 would be the amplitude of motion, right? If I had x equal to a sine square omega t, this I could write as a by 2, 1 minus cos 2 omega t. Is this simple harmonic? Yes, yes. This also is simple harmonic with amplitude being a by 2 and angular frequency being 2 omega. Angular frequency being 2 omega. Clear? If I had x equal to e power omega t, is this simple harmonic oscillator? Okay, let's see. X dot is omega e power omega t, right? X double dot is omega squared e power omega t. But e power omega t can be written as x. So this is omega squared times x. Is it simple harmonic? No. Where is the minus sign? Where is the minus sign? It's not simple harmonic. X double dot is proportional to x. It's not restoring in character. Right? So this is not simple harmonic. It has to be minus omega squared times x plus a constant x. Right? If I had x equal to p sine omega t plus q cos omega t, will this be simple harmonic? x equal to p sine omega t plus q cos omega t. Is that going to be simple harmonic? It will be? Why? No, I will not differentiate. Yes, you can do that, but I will not do that. Because realize that I could write this as root p square plus q square way back in trigonometry. Right? And this I can write as some cos phi. This I can write as some sin phi. Yes or no? We learned this in Trigo. This is cos phi, then this would be sin phi. So if I choose this as cos phi, this then perforce would be sin phi, which would make it sin A cos B plus sin B cos A. So sin A plus B. So this is root p square plus q square sin omega t plus. This is not simple harmonic. What's the frequency? Angular frequency? Omega. What's the amplitude? Root p square plus q square is the amplitude of the motion. Right? Yeah. However, if I had x equal to p sine omega t plus q cos omega prime t, this will not be simple harmonic in my mind. By differentiating different things, it will not be simple harmonic. You find that the two constituents have different omegas, close your eyes and conclude that it's not going to be simple harmonic. So far, so good. Now, it's important to understand, extremely important to understand uh, certain things about a simple harmonic oscillator. Number one, which I have already established, from f equal to minus kx, we started and we chose omega as root k by m. That was by choice. Until then, we knew nothing about omega. We didn't know that, well, it will be related to the time period as t equal to 2 pi by omega. We didn't know that. We just used it as a symbol for root k by m. That's all, right? It so happened that 2 pi by omega also turned out to be the time period of motion. Now, for a given oscillator, this k and therefore also k by m and therefore also root k by m, which is omega, like I mentioned at the very onset, is a very innate property, fundamental property. We can't do anything about it. For a given oscillator, we'll have to live with that root k by m or an omega, right? Now, how do we determine this root k by m? Therefore, k, given the mass, how do we determine the force constant for the motion. The force constant for the motion. Now it depends on the physicality of the situation. A simple harmonic oscillation could be obtained in very many ways. One of the ways of obtaining a simple harmonic motion is the following. This is a spring attached to a mass m, and the spring is in its natural state. Natural state. That means unstretched length. Unstretched length. And let's say the spring constant is k. In this case, the spring constant is k. I'm not saying the force constant of the motion. For the time being, it's only the spring constant that I'm referring to as k. It's an ideal spring that we'll assume, and the whole system rests on a frictionless surface. And I choose to call this position of the mass as x equal to 0. I choose to call this position of the mass as x equal to 0. Now, very slowly, I deviate the mass from this position. When I say very slowly, it means that in an unaccelerated manner. In a manner that the mass does not develop any velocity. Mass does not develop any velocity. That's what I mean by very slowly I pull the mass, say, to the right, causing the spring to get stretched beyond, over and above its natural length. Say by an amount x. X to the right. So the spring has an extension x over and above its natural length. Since I have pulled the mass very slowly to the right at every instant of time, the external force that has pulled the mass has only managed to balance the spring force so that the net force acting on the mass m was 0 at all times. And then I release this mass. But one thing for sure, when the mass is displaced by an amount x to the right and it's left to go on its own, it experiences a force kx to the left. It experiences a force kx to the left. This force is proportional to the displacement from this position. This force is proportional to the displacement from this position and is always directed towards this position. Is always directed towards this position and therefore could be looked upon as a restoring force. And therefore, if the force is proportional to displacement from a certain position all the time and is always directed towards that position, then the nature of motion that it's going to produce would be simple harmonic, right? So one thing for sure, I can describe the force acting on, once it's released from this point, force as minus kx, which would obviously produce simple harmonic motion. Now it's only in this situation that the force constant of the motion coincides with the spring constant of the spring, right? And the omega for this motion, so once you have established f equal to minus kx, you can conclude that the motion is simple harmonic, and the angular frequency of this oscillation is going to be root k by m is going to be the angular frequency. The time period is going to be 2 pi by omega and so on and so forth, right? But this f equal to minus kx does not tell me anything about the amplitude of the motion. It tells me about the frequency, it tells me about the time period, the omega, everything, but not about the amplitude. Now, once you have established that a certain motion is simple harmonic, then identify 2 points in that motion. One, a point where the net force acting is 0. In that motion, identify 2 points. Point 1, where the net force is 0, and that point would be referred to as the mean position. This would give me the mean position. The position where the net force is 0 would be the mean position. Right. And then identify a second point where the velocity of the particle is, where the velocity of the particle is 0. And that position would be an amplitude position. Right? Now, in a situation of this kind, the SHM will get executed only after I let go the mass, right? So now at this juncture I let go the mass, and then it will be subject to a force description of this kind, causing the motion to be simple harmonic with omega being this and t being this. This position then is the point where the velocity is 0. This position is the point where the velocity is 0. So this position would be referred to as the amplitude position. This position is the point, after all, when the mass gets restored to this position, it would have acquired a velocity under the influence of an accelerating force, but the force at this juncture acting on the mass would be 0. Why? Because the spring would be in its natural state and the net force acting on the mass is going to be 0. So this must be the mean position. And the separation between the mean position and the extreme position will give you the amplitude of motion. Right. So then, this mass m, and it's very slowly pulled to the right. Let's say by an amount 5 centimeters, very slowly pulled to the right by an amount 5 centimeters and release. What then would be the amplitude of motion? 5 centimeters. If it's pulled by an amount 10 centimeters and then released, slowly pulled by an amount 10 centimeters and then released, what would be the amplitude? 10 centimeters. But in each of these cases, be it 5 centimeters or be it 10 centimeters, what would be the omega of the oscillator? Root k by m. It will not depend on the amplitude. Do you realize that? Right? So these are two different things. You have the choice of giving the amplitude. You can pull it very slowly to the right by an amount 5 centimeters and you will produce an amplitude of 5 centimeters in the oscillator. Or you can produce an amplitude of 10 centimeters in the oscillator. But can you change the omega of the oscillator? Because k will not change. We will assume that this mass is constant until and unless, well, you have a mass with a leakage and you force this mass is just a sandbag, then m will change. We will assume that that's not the case. Or you can change k if you pour acid on this and it dissolves. Right? We are assuming that you're not going to carry out such nefarious activities on the spring or the mass. So omega will then be retained as fundamental to the oscillation. Right? We have handle over the amplitude, but we don't have handle over the omega or the time period. That's going to be the same for a given system. The system is, the mass and the spring is one system. Of course, if you add another spring to it, then the system will change. That's not the same system. So for a given system, that means the same combination of m and k, you can't change the omega or the time period, but then you can change the amplitude. So the amplitude is your choice. The omega is determined by the system inherently or innately. Clear? Now, I vary this a little bit. What I did so far was I pulled this mass to the right very, very slowly and then release. Pulled this mass very, very slowly and then I release. And subsequent to the release, I observed that the motion executed was simple harmonic. The mass was left at the mercy of the spring, which executed a F equal to minus kx and routinely produced omega equal to root k by m, and you determined the amplitude and let go the mass, right? Let me alter this, modify this a wee bit. Suppose I give this mass an impulse. At this juncture, I give it an impulse. That means a blow. And I release the blow. And the mass develops a velocity v0. The mass develops a velocity v0. The mass release the blow, I give it a velocity v0 and I release it. And I let go the mass under the influence of the spring alone. Well, so at this point, the force acting on the mass is 0. The force acting on the mass is 0. And as the mass keeps moving to the right, let's say, call it x equal to 0. As the mass keeps moving to the right, the spring will keep pulling the mass to the left, so will keep killing the velocity of the mass. So after a while, when the mass would have got displaced by an amount x to the right, it would experience a force kx, which is restoring and leftwards, which is restoring and leftwards. So the motion will obviously then be simple harmonic. The motion will still be simple harmonic. And the omega of the motion will be root k by m. The time period will still be 2 pi by omega, right? Because f will still be minus kx. It will not depend on this v0. It will not depend on this v0. But then what this v0 does is, it will determine the amplitude of motion. Realize that if the motion is simple harmonic, then this point is the point where there is no force acting, and therefore this must be the mean position. This must be the mean position. The omega of the motion is known. The omega is root k by m, which is known. And the velocity at the mean position is given by omega times a. The velocity at the mean position is given by omega times a. So given v0, omega obtained from this, the amplitude of the motion could be obtained. The amplitude of the oscillator can be obtained. Clear? I could have also done the following. I could have stretched the mass by an amount x naught. I could have stretched the mass by an amount x naught, spring by an amount x naught, and I could have imparted it a velocity v naught. I could have imparted a blow v naught to the right and then let go the mass. Again, once I let go the mass would be subject to F equal to minus k times the displacement from the mean position. The motion will still be simple harmonic. The omega of the motion will be root k by m, etc. But what about the amplitude of the motion? Okay. Well, what's the total mechanical energy that I leave the system with? Half m v naught squared plus half k x naught squared. That's the energy that I leave the oscillator with. This is the total energy at all times. This is the total energy at all times. At the amplitude position, it will only be half Ka squared. At the amplitude position, it's simply going to be half Ka squared. So the amplitude of the motion can be obtained. The omega will still be root k by m and so on and so forth. Yes or no? This will still be the mean position because no force acts at this point. Now, another variation to this could be the following. This is the natural state of the spring. And let me call this point x equal to 0. And now I subject this mass to a constant force F acting to the right. I subject this mass to a constant force F acting to the right. A constant force F acting to the right. So in which case, is this the mean position? No, because the net force acting at this position is not 0 but F. So this is for sure not the mean position. But then even before I talk of the mean position, let me at least be convinced that the motion would be simple harmonic under the influence of this force. Right? Let's do that first and then talk about the mean position or the amplitudes, etc. Right? Now, while it moves under the influence of this force, the spring stretches. The spring therefore resists the motion to the right. The acceleration to the right of this mass will decrease because the spring force is increasing, this force is remaining constant. However, as long as the external force is larger than the spring force, the acceleration would be to the right and the velocity will keep growing. The velocity will keep growing. Now, after a while, let's say when this force has successfully displaced this mass m by an amount x to the right, then at this instant, the forces on the mass m, f to the right, and let's say this is x equal to 0, this is x, and kx to the left. The net force acting on the mass to the right, the F net acting on the mass to the right is going to be F minus kx. Is going to be the net force acting to the right. Now, obviously, you can find a value of x where this F net becomes 0, right? Say x equal to x naught, the force is kx naught, and let's say at this point the F net becomes 0. At this point, F net becomes 0. So F net is 0 at x equal to x naught equal to F by k. F net is 0, right? That means at x naught equal to F by k, the particle is subject to no net force, Okay. Now, just move the clutter. this is a point, x naught equal to F by K, then the external force is balanced by the spring force. Is balanced by the spring force, right? Now, look at the following. With respect to this position, I displace it additionally by an amount delta x. I displace it additionally by an amount delta x. That means now the spring force is going to be K x naught plus delta x, because the net elongation in the spring is x naught up to this point plus delta x, right? So which means the spring force acting is going to be x naught plus delta x. This is the net leftward spring force at this point, right? So then the net restoring force acting on the mass m is going to be this minus F, right? The F restoring would be of magnitude, the F restoring would be of magnitude K x naught plus delta x minus F leftwards, minus F leftwards. But Kx naught is the same as F, Kx naught is the same as F. So this Kx naught cancels this F and you have K times delta x, because Kx naught is F. That means the restoring force from this position, there is a certain position where the net force is 0. Now with respect to this position, if I additionally displace it, then there is a restoring force acting on this mass, which will be proportional to the displacement from this position, which is an equilibrium position, position of no net force. So can I not conclude that the motion is simple harmonic, because force is proportional to this and is restoring in character, Can I say that? And the force constant is K for the motion. So the omega for the motion will still be root K by M. The omega for motion will still be root K by M. The time period is going to be 2 pi by omega. These are ready reckoners and this will not depend on F. The system does not give handle over omega to anyone, right? So like the earlier case, the omega will still be the same. It will execute simple harmonic with an omega equal to that and a time period equal to 2 pi by omega. Now the question is, we've identified the motion to be simple harmonic. We've understood that it will have a time period this and the omega that. We then need to address what the amplitude would be. Under the influence of, yes or no, right? We need to address what the amplitude is going to be. So let's work on the amplitude aspect of this oscillation. Under the influence of a constant force F, F, in this case to the right. Okay. So we've already found that, well, there can be a motion where the natural state of the spring does not mean that that's going to be the equilibrium position. The natural state of the spring need not necessarily be the equilibrium position. In this case, the equilibrium position or the mean position has got shifted by an amount x naught with respect to the natural state of the spring, right? So the amplitude issue remains pending. Okay. So see how we can hash out the amplitude of this motion. there is this x equal to x naught, this is x equal to 0, this is x equal to x naught, which is an equilibrium position or a mean position. X equal to x naught is an equilibrium position or a mean position for sure. Now, one thing that we can very readily see is that this was the point where there was no velocity, right? So this you can expect to be the amplitude position. This is the main position, and therefore would you not believe that x naught is the amplitude of the motion? Do you not believe that x naught is the amplitude of motion? Right away we can say that x naught, which is f by k, is the amplitude of motion. Now, where did that come from? Switch off. All right. Like I said, x naught equal to f by k is the amplitude of this motion. This is the mean position at x equal to x naught. We could also have done things kind of independently, in the sense that at this point v was 0, force acting was to the right? At this point also the velocity was 0 and the force acting to the right F, and there was a spring force Fs, right? So this mass in its journey from P to Q was acted upon by two forces. The external force F, which was a constant force, and the spring force, that was a variable force, right? I can apply work energy theorem between P and Q. Right. Let's say P and Q are separated by an amount L. P and Q are separated by an amount L. So then, what's the work done by F? What's the work done by F? F into L. Why do you look so tentative? F into L, isn't it? F into L is the work done by F. What is the work done by the spring force? I've told you kind of 135 times that the work done by the spring force will always be negative of the change in elastic potential energy. Work done by the spring force will be negative of the change in elastic potential energy. Right? Elastic potential energy is 0 here. Elastic potential energy is half KL squared. So negative of half KL squared would be the work done by the spring force, right? So work done by the spring force is minus half KL squared, and that must be, from work energy perspective, change in kinetic energy. What's the kinetic energy here? What's the kinetic energy at this extreme? 0. So change in kinetic energy is 0. Right? And this clearly gives me L equal to 2F by, which is 2 times x naught. You realize that this is 2 times x naught? X naught was F by K, right? That means this length is x naught, this length is x naught, which is only a confirmation that x naught must have been the amplitude of this motion. Clear? Once I have determined the amplitude of motion, can you then tell me what's the velocity at the equilibrium position V naught? What's the velocity at the mean position? Omega times the amplitude. Omega times the amplitude. Yes or no? So the velocity at the mean position is going to be omega times x naught. X naught we've already determined. And omega is root k by m. Omega is root k by m. So the velocity at the mean position is given by omega times x naught. Omega known, root k by m. X naught we have calculated as f by, right? Also between P and R, let's say, we could have applied work energy theorem to calculate V naught. Between P and R, we could have applied work energy theorem to calculate V naught. So then, if I apply work energy theorem between P and R, what's the work done by F? F into X naught? That's the work done by F? Work done by the spin force. Minus half kx naught squared, minus half kx naught squared, negative of the change in elastic potential energy. That's going to be the work done by the spin force, right? So minus half kx naught squared. And that must be the change in kinetic energy. So half mv naught squared minus 0. X naught is known, F by K, and V naught could also have been obtained from these considerations, which would then turn out to be the same as omega into X naught, right? You could have had something like this. A spring with force constant K and a mass M attached at one end of the spring, and initially at rest, there was an identical mass M which was moving with a velocity V naught to the right, and the whole system rests on a frictionless surface. This mass A collides with this mass B in a perfectly inelastic manner. Perfectly inelastic collision. Which means after the collision, the two stick together. So just after collision, the combined mass is 2m. They move together as one lump mass. With a velocity v common, vc, right? And then it's going to, so this is the, let's say, the natural state of the spring. This is the natural state of the spring. This natural state of the spring, which means the spring will get compressed, the spring will get compressed in this direction, and it will exert a restoring force on the mass in this direction proportional to the extent of compression. So we know for sure that the nature of motion executed is going to be simple harmonic, and if this is x, the force would be like a kx leftward for any given x. So the force constant of the motion is k. It's not just the spring constant, it's also the force constant of the motion. So the omega of this oscillation is going to be root k by m, right? K by 2m, sorry, the mass is 2m now, k by 2m. K by 2m is the omega of the motion, k by 2m, root k by 2m. The Vc can be obtained by preserving linear momentum. So this mass and this mass, just before collision, had a total linear momentum mv naught. Just after collision, it became 2m into Vc, conserving linear momentum, giving me Vc equal to V naught by 2. So then, there are two ways of calculating the amplitude. There are two ways you could deploy to calculate the amplitude. One is, well, this you realize is zero force acting on the mass 2n, right? So this must be the mean position or an equilibrium position, right? So Vc here is going to be omega times amplitude. Vc is going to be omega times the amplitude, and Vc we have already calculated as V naught by 2. So Vc is omega times the amplitude. Omega is known, root k by 2m, the amplitude could be computed because Vc is V naught by 2. One way to calculate. One way to calculate. The other thing that you could have done is, well, at this point, when simple harmonic motion just got initiated, the system had only kinetic energy, half of 2m into Vc squared. Right? And when it got compressed by a maximum amount, that means when it came to its amplitude position, then it had no kinetic energy. There was only elastic potential energy in the spring, which is half Ka square. Half. This entire kinetic energy got converted into elastic potential energy of the spring in the amplitude position as half K square. So A could also have been computed with this. It's going to be the same thing. It's going to be the same thing. No big deal. Because see, realize that this K by 2m is actually omega squared. Yes, you can. Of course, you can deploy. Only thing is, it becomes kind of hellish to deal with it because you have a variable acceleration case, variable force. You can deploy Newton's second law. Why not? It's going to give you the same thing, except that it will get scaled up in magnitude. That's all. Suppose let me modify this situation again slightly. This mass was executing simple harmonic motion, already executing simple harmonic motion, and say it was executing simple harmonic motion with omega, of course, would be root k by m. At some instant, well, this is the natural, this position reflects the natural state of the spring. This position reflects a position where the spring was unstretched. So that means in this state, the spring is compressed. The spring is compressed. Let's say the spring is compressed by an amount x1. The spring is compressed by an amount, and the mass m has a velocity, say v1 to the right. The mass m has a velocity v1 to the right in this state. And at this point in this state, it's struck by another mass m, which was moving to the right with a velocity v0. It was struck by another mass m, which was moving to the right with a velocity v0. This mass. So first things first. Before this mass got embedded into this mass, we will assume that there is a perfectly inelastic collision, so that the two coalesce as one single unit and they forge to the right for a revised motion. But well before this collision occurred, the omega of the motion was this. So call it omega initial. Prior to the collision, this was the angular frequency. The time period was 2 pi by omega I, etc. What was the amplitude of motion? Okay. The system has a total amount of energy, half mv1 squared plus half k x1 squared is the total amount of energy housed by the system, by the oscillatory system, right? The system means m and the spring put together, right? So half m v1 squared plus half k x1 squared. Half m v1 squared plus half k x1 squared, and in the amplitude position, this energy appeared as half k squared. In the amplitude position, it appeared as half k squared. Yes or no? Let's say A initial. So this would enable computation of the initial amplitude. Prior to the collision, this would be the initial amplitude, right? So we know the initial omega I, the initial amplitude. Subsequent to collision, I want to compute the new omega and the new omega and the new amplitude. Now, as far as the new omega is concerned, k remains the same, only m becomes 2m, right? So the omega nu in the post collision period, the motion will still be simple harmonic. The only thing is the omega nu is going to be root k by 2m. This is going to be omega nu. The two masses just after collision at this instant would move as one unit 2m kilograms with a velocity vc. Just after collision, let's say they have a common velocity vc. Now, to calculate vc, I preserve linear momentum in the horizontal direction. So just prior to collision, I had like a mv0 plus mv1, right? M into v0 plus v1. Just after collision, it's going to be 2m into vc, 2m into vc. So this enables calculation of the common velocity at x1, right? No. Give me flaw in this calculation. Tell me the mistake. Yes, because there is a spring force which is an external force. Spring force which is an external force, horizontal, is not zero, and therefore, very strictly speaking, the linear momentum in the horizontal direction is not necessarily conserved. Linear momentum is not necessarily conserved. Yet I would want to stick to this. I'm saying that, well, I have made a mistake, but I will still want to stick to this. Reason being, when the two masses collide, the force of collision is huge, humongous. The forces that they exert on each other along the common normal is very, very large. And it's much larger than the spring force. And in light of this, the spring force could be neglected. And it would be justified carrying out this calculation. It would be an approximation for sure, but it would be a practical approximation. It's fine to do. Spring element will not respond enough to change the linear momentum all by itself during that short time of collision. In that short time of collision, yes, the linear momentum is not conserved, but the manner in which the spring force will change the linear momentum is spring force into delta t. That would be the change in linear momentum that the spring force could incorporate in the system. But then that spring force is so small that Fs into delta t, the impulse of the spring force will bring about a negligible change in linear momentum, and therefore preserving linear momentum is a fairly good idea for a situation. So technically it's not absolutely correct, but then practically it's fine to do, right? So this we can apply given that the colliding forces are much larger compared to the spring force. So the only participating forces are the colliding forces, which will only redistribute the total linear momentum, will not bring about a change in linear momentum, whereas the spring force is potentially capable of changing the linear momentum by an amount, spring force into delta t, where delta t is the time over which the collision occurs. But then, since that delta t is very small and that Fs is very small, spring force is very small, Fs into delta t, the change in linear momentum brought about by the spring force alone is a negligible entity, which we can dump. Therefore, we go ahead and still apply conservation of linear momentum for that small period of time, delta t, which the collision occurs. Okay, having said this, then, this is the new Vc. At x1, the new omega is this, and this gives ground for calculation of the new, because at this point the spring force will still be half k, the elastic potential energy will still be half k x1 squared. The kinetic energy of the system is going to be half 2m into Vc squared, where Vc is that, right? And in the amplitude position, this entire thing gets converted into half ka squared, right? This x1 becomes a and this Vc becomes 0, right? This is half ka squared, So the amplitude of the motion can be obtained regularly, right? Look at a vertical spring. Force constant K. Let's say this is the natural length of the spring, unstretched state of the spring, mass m of the spring, and a palm is holding the mass m. Right? Now, the palm is slowly brought down. Till such time that the spring force balances mg. In this case, if the palm was not there, realize that there is mg downwards and there is spring force which is 0 here, right? So now I just use my palm so that the mass m on its way down does not get accelerated. I allow the mass m to very slowly drift downwards. Very slowly I allow it to drift downwards. By an amount x naught, such that the spring force kx naught balances in very slowly. That means by the time the mass has reached this position, it has not gathered velocity. So kx naught is mg. So this is like an equilibrium position where the net of all forces is 0. So this is the natural state, this is the equilibrium position where F net is 0. Now, very slowly I remove my palm. What happens? Nothing happens. It will stay there because it has not gathered velocity to drift downwards and no acceleration either for it to gather velocity. right? So it will just stay there. Just because I said what happens does not mean something has. But you can make certain things happen. What you do is, now, very slowly one scale, right? Very slowly you pull the mass M down by an amount X. You pull it down by an amount X. Very slowly you pull the mass M down by an amount. Realize that the spring force then is going to be K times X plus X naught. K times X plus X naught, and the weight will still be mg. But this Kx naught will balance mg. So you will be left with a net unbalanced force Kx upwards. You will be left with a net unbalanced force Kx upwards. So from the equilibrium position, the position of no net force, this is the position of no net force. If the mass is displaced slowly by an amount x downwards with respect to the equilibrium position, it experiences a net force Kx upwards. It experiences a net force Kx upwards. Very clearly, it's a restoring force. And the magnitude of this force is proportional to the extent of displacement with respect to the equilibrium position. The motion then must be simple harmonic. The omega of the motion must be root k by m, because the force constant turns out to be k. So the omega of the motion will be root k by m. Right? Now, and this whole thing has been done very, very cautiously. The mass is pulled down very, very slowly, and then it's released. So force will be proportional to displacement. What about, so motion simple harmonic with this as the equilibrium position. Again, the natural state of the spring is not defining the equilibrium position, because that's not a state of no net force. The net force here is mg downwards. It's not zero. This is a state of no net force, and this therefore is the equilibrium position, right? Motion is simple harmonic because from the equilibrium position, when you place it by an amount x downwards, it will experience a force kx upwards, commensurate and in line with the requirements of simple harmonic. What would be the amplitude of motion? Yes, suppose I pull it down by an amount 3 centimeters. This is zero velocity state, and this is the equilibrium position. So between the equilibrium position and the zero velocity state, you're going to get the amplitude. So the amplitude is going to be 3 centimeters. If you had pulled it down by an amount 8 centimeters very slowly, then the amplitude would have been 8 centimeters. But in each case, the omega will be root k by m. Root k by m. Right? No issues with this. Let me change this slightly. Vertical spring, but now I will alter the looks of this. No palm holding the mass M. Okay, initially I am holding it, right, like this, and I very abruptly withdraw the palm. Very abruptly withdraw the palm. When I abruptly withdraw the palm, then the mass M feels helpless because it's at the mercy of gravity. mg then pulls it down. At this juncture, the spring force is like non-existent because the spring is in its natural state. So mg takes over and the mass begins to descend downwards, and only after a while the spring responds. It will exert an upward force, right? But for a certain time, mg would be larger than the spring force. The mass will continue to develop a downward velocity, at each instant under the influence of an acceleration which would be caused by the difference of mg and the spring force, a variable acceleration. Because the spring force is varying, not mg. Right? So after a while, the mass m comes down. And it gets displaced by an amount x naught. But then by the time it reaches this position, it would have also acquired a velocity v naught. It would have acquired a velocity v naught, unlike the earlier case. In the earlier case, I was tampering the mass m downwards. But now the mass was left wide. So it came down with momentum, velocity v naught, right? Now x naught such that kx naught is mg. Such that kx naught is mg. So then this position would be a position of no net force on the mass m. This would be a position of no net force on the mass m. So this I can refer to as an equilibrium position. Equilibrium position. No net force, so what? Does it mean it's not going to move down any further? No, it will. Because of inertia. V naught onwards, so it's still going to move down under the influence of inertia. Inertia. Not gravity, because gravity has been countered by the spring force. So inertia. Because of inertia, it will move down. Now, when it moves down, let's say at some instant, it would have moved down by an amount. It would have moved by an amount x. X with respect to the equilibrium position, it would have moved down. At this instant, the spring force is going to be k times x plus x naught, and gravity is going to be mg downward. Kx naught will balance mg. Kx naught will balance mg. The unbalanced force is going to be kx upward. So it will be towards the equilibrium position, and it will be proportional to the displacement with respect to the equilibrium position. So the nature of motion will still be simple harmonic, with the force constant still being k, and therefore the omega of motion is going to be root k by m. Got me? Now, how much will it go down? How much will it go down? How much will it go down? This was, let's say, a reference line, and we want to figure out how much it could go down, right? Yes, you're right, but let's be sure about that. The maximum descent that it could naturally have, the maximum descent that it could have, let's say this was the original position, initial position I, let's say this is the final position. It would keep going down until such time that its velocity becomes 0. So this initial position, the velocity was 0. This final position, velocity was 0. And it went down by an amount L. It went down by an amount M. So between these two states, I can apply work energy theorem. Work energy theorem. There was one constant force acting mg. There was one constant force acting mg, and the work done by mg was mg into L. And then the elastic potential energy of the spring here was zero here, because the spring was unstretched. Elastic potential energy was 0 and was half KL squared here. So the work done by the spring force must have been minus half KL squared. And this must be change in kinetic energy. 0 minus 0. So very clearly, L then becomes equal to 2 mg by K. Right? Which is 2 times x naught. As you can see, it's 2 times x naught. where x naught is mg by k, where x naught is mg by k. So the amplitude, this entire thing is L, which is 2x naught. This is x naught, this is x naught. Evidently, the amplitude of motion is going to be x naught. The amplitude of motion is going to be x naught, right? Which would be mg by k. In the earlier case, realize that we had handle over the amplitude. But in this case, if I release my palm here, then Mother Earth will decide what the amplitude would be like. It's going to be mg by k, the amplitude. You can't change the amplitude here. In this case, the amplitude is also built in, the omega is also built in. In the earlier case, the amplitude could be altered at will. The earlier one, from the equilibrium position, I deviated by 5 centimeters slowly and released, the amplitude would be 5 centimeters. But in this case, I left it right here, so it didn't bother about me. It said, all right, so I'll have my amplitude my way. So it says the amplitude built into the system is going to be mg by k. The omega will still be the same, root k by m. So these are two different states of a vertical spring. Realize that. One, where at this very state, I let the mass go its own way, right? And it develops an amplitude and so on and so forth. In the earlier case, I escort it till equilibrium position and then I let it go. It doesn't do anything. It respects me. And then it says, all right, you've done so much for me. You've brought me to the equilibrium state, the earlier one. Now you can decide my amplitude. So then I say, all right, 3 centimeters or 5 centimeters or 6 centimeters. But in this case, if I release it right here, it says get lost. My amplitude is going to be mg by k. Mother Earth takes over, right? Now, I know the kind of sentiments that brew in you at this point of time when I turn around. You know, there is heavy mental activity going inside you. There is a suspense which is running very aggressively through all your veins, nerves, and your mental energies are only directed at determining, oh, is he going to fall off or is he going to continue? And then, while your heart palpitates, your mind tosses. It says heads, he continues, tails, finishes. And in the midst of this, when I turn around to take a quick glance and stock of your expressions, they speak volumes about what you're thinking. For a moment, I get drawn and disturbed. Hey, maybe, I should take mercy. And then next moment, no, yeah. So at this point of time, that no, yeah is predominant. Sorry, I have to withdraw your smiles. So you're not going to die if you're here for some more time. All right. Tandem style. It's we're not too far away from the 1st of January, and therefore, I would still like to maintain some grace. I have such wonderful expressions that are, getting carved inside me, and they're waiting to inundate you. But only thing is, uh, eventually, when I look at you, you look innocent. All right, and that just prevents me from crossing the borders. Otherwise, I would take liberty to cross the LOC. And I would pounce on you in one moment, right? Okay. So preserve your vocal energy for better usage at a later instant of time in real life. All right. Otherwise, I'll make your real life imaginary. Okay. There is a settled system here. with mass m1 and m2 on top, and it's at rest. It's at rest. Naturally, the spring couldn't have been relaxed in this state. Spring, the spring force must have balanced the m1 plus m2 into g. Right? The natural state of the spring must have been somewhere here. The natural state of the spring must have been somewhere here, and the spring by this time would have got elongated by an amount x naught, such that kx naught acting upwards balances m1 plus m2 into g downwards, right? Now, what I do is I take this mass away from the system. Mass m2 is taken away, removed. It was sitting happily, and suddenly I remove m. I remove m. When I remove m2, the spring force will still be kx naught, and it happened to have balanced m1 plus m2 into g. If I remove m2, then the net downward force will be m1g, and the spring force will become larger than m1g. The spring force will become larger than m1g, and therefore the system would move up. System would move up under the influence of a net force, spring force minus m1g. Spring force minus m1g under the influence of this force is going to travel upwards. It's going to travel upwards. So if I remove the mass m2, this mass m1, would come somewhere here, and by an amount should move up by an amount x, so that the net spring force in this state is k times x naught minus x, right? Because now the extent of elongation of the spring is x naught minus x. So k times x naught minus x, right? Just balances m1g. Where x naught is known to us, and x, the new equilibrium position, this x will determine the new equilibrium position. Or what you can do is, just to make life a little simpler, I can call this as x, so that the spring force will now at this point be only kx, So this kx balances m1g. Are you lost with this, or are you fine with this? Right? So I choose this as x so that the spring force looks kx, right? So kx in this case just balances m1g. This x is the new equilibrium position. X naught was the earlier equilibrium position. Right? X naught was m1 plus m2 into g by k, and x is m1 into g by k. Again, this will still execute simple harmonic motion with omega equal to root k by m, and what would be the Hey, when this mass goes from this state to this state, This is a state of zero velocity. So this must be the amplitude state, and this is the equilibrium state. That means this must be the amplitude of motion. The amplitude of motion therefore must be x naught minus x must be the amplitude of motion, yes or no? So the amplitude here is going to be x naught minus x. X naught minus x means m1 plus m2 into g by k minus m1 into g by k. So the amplitude is going to be m2g by k. So if you remove the mass m2, it leaves its trail behind. It says, all right, leave me behind, but you will have to move with the amplitude that I set for you, m2 into g by k, right? So that's going to be the amplitude. The omega is going to be root k by m. Got me? Can I back this up? Akbar, stand by. Right. Say there is a platform. And there is a mass m on the platform. There is a mass m on the platform. And the platform is made to execute simple harmonic motion. Platform is made to execute simple harmonic motion between these two limits. Amplitude A and angular frequency omega. The platform is made to execute simple harmonic motion between these two limits. Amplitude A and angular frequency omega. Now, the mass m, as long as it stays in contact with the platform, it will execute simple harmonic motion with the same amplitude and with the same angular frequency. Clear? Now, at some point when the mass m, this is the equilibrium position. At some point when the mass, when the platform is say x units above the equilibrium position, then the force acting on the mass m, would be what? Mg downwards and normal reaction from the platform upwards. Mg downwards and normal reaction from the platform upwards. Since the mass is executing simple harmonic motion, Mg minus R must be providing the required force Kx downwards. It will need a force Kx downwards. The mass M would need a force Kx downwards, yes or no? Right? That means, where does that Kx come from? For it to execute simple harmonic motion, the net force acting on the mass M must be Kx downwards. So then, Mg minus R will be responsible for the Kx. Be responsible for the K force Kx. The normal reaction R then is going to be Mg minus Kx. The normal reaction R is going to be Mg minus Kx. Now, in contrast, at some point, let's say when the platform was x units below the equilibrium position, say when it was x units below the equilibrium position, this is above when it was x units above the equilibrium position. Next, when it's x units below the equilibrium position, below EP. Now the forces are mg and r. Forces are mg and r. Now, what provides a mass m the required force to execute simple harmonic motion? R minus mg. In this case, it's R minus mg. That must be kx. Upwards. It has to be upwards when it's displaced downwards. The restoring force has to be upwards towards the equilibrium position. So R then is mg plus kx. Right? Which means below the equilibrium position, R can never become 0. You realize that? Below the equilibrium position, R can never be 0. That means if R never becomes 0 below the equilibrium position, it implies that below the equilibrium position, contact is never lost. R equal to 0 is a state governing loss of contact. So while this executes simple harmonic motion, there is no possibility of the mass m to lose contact below the equilibrium position. The mass m can never lose contact below the equilibrium position. So the positions below the equilibrium positions are not weak states, are not vulnerable states in as far as maintaining contact is concerned. No matter what we do, contact will always be maintained for any A and for any omega below the equilibrium position, right? However, above the equilibrium position, R could become 0. R could become 0. Right? Above the equilibrium position, R could become 0. Now, this is the amplitude position. Realize that as x increases, R decreases. So if R does not become 0 at the amplitude position, it will not become 0 anywhere, because that's the weakest point, right? If it's not 0 at the amplitude position, because at the amplitude position it's the least, x is A, largest, x is largest. So at the amplitude position, R is the least. And if it doesn't become 0 at the amplitude position, it will not become 0 anywhere. Clear? Now, what we really want is, for this to not lose contact, we want to ensure that it doesn't lose contact above the equilibrium position. We don't have to bother about positions below the equilibrium position, because above the equilibrium position, R could become 0. Below the equilibrium position, R could never become 0. So for it to not lose contact, R must be greater than or equal to 0, let's say. For it to never lose contact, R must be greater than or equal to 0. That means mg minus kx must be greater than or equal to 0. Yes, that means x has to be less than or equal to mg by k. X has to be less than or equal to mg by k. That means the maximum displacement above the equilibrium position should not exceed mg by k. The maximum displacement, this x is displacement above the equilibrium position, and it should never exceed mg by k. That's what it means, yes or no? Right? That means, but m by k is 1 by omega square. M by k is 1 by omega square. So this gives me x less than or equal to g by omega square. So the displacements above the equilibrium position should not exceed g by omega squared in order that contact is sustained. So if the amplitude itself is less than g by omega squared, then all the x's will be less than amplitude. They will also be less than g by omega squared. So then the condition that will guarantee maintenance of contact is A less than or equal to g by omega squared, because A is the maximum x, and if the maximum x itself is less than or equal to g by omega squared, then all other x's will be less than g by omega squared, and there would be no possibility for it to lose. Right? So this is important. This relationship is extremely important. It's used in MCQs time and again. So if this is executing simple harmonic motion with amplitude A and angular frequency omega, I better ensure that A is less than or equal to g by omega squared for contact to be maintained all the time. Right? Sometimes what they do is they say, well, we are reluctant to change the amplitude, but we can compromise with omega. We are reluctant to change the amplitude. We need this amplitude for this physical situation, but we can compromise with omega. That means I do need to go 5 centimeters up and 5 centimeters below the equilibrium position, but then I'm ready to nudge with the omega. So then what they say is, all right, if you are ready to nudge with the omega, then you better ensure that omega squared is less than or equal to g by a for it to maintain contact. Okay? I mean, amplitude can be given to be whatever the system requires. But then in that case, you would have to compromise on omega. Omega should not exceed root g by a. Right? But then in a situation where you say, well, I can't compromise with the omega, then you compromise with a. Then you say a less than or equal to g by omega squared for it to maintain contact. Right? This is important. A less than or equal to g by omega squared. In fact, the vertical spring situation that I just demonstrated to you was a real life simulation of the same thing. You know, there was this mass m1 and this was mass m2 resting on it. So it was the same thing. It was like a platform of this kind and a mass m2 resting over it like this, right? And then in order that m2 maintains contact with m1 all the time, we must have a less than or equal to g by omega square, where omega in this case is predetermined to be root k by, omega is root k by m1 plus m2. Omega in this case would be root k by m1 plus. So then you will have to sacrifice the amplitude. Realize that? So this is exactly the same as this, where this m1 is the platform and the platform is given simple harmonic motion by the spring. A less than or equal to g by omega squared is the governing principle here. Right? No. Actually, I would have realistically liked to carry on for some more time, but I can see that, you may not necessarily assimilate everything that I say beyond this. We've just gathered momentum. I would have liked to spring into action at this point and give you more amplitude, but the time period is limited. We were therefore meet tomorrow. Now my agenda for tomorrow. Hello.